Welcome everyone, my name is Dr. Ulf Henning Richter. Today I would like to present on how to implement science-based climate targets. The global warming projections look dire. At present, if we continue on our current path, warming is projected by the end of this 21st century to be at 2.7 to 3.1 degrees Celsius. If we take into account the current pledges and targets of governments and organizations around the world, it would be 2.4 degrees Celsius. If we're being optimistic about net zero targets, maybe we might end up with a 2.0 scenario. However, in the Paris agreements, governments and organizations around the world agreed on a 2.5 degrees Celsius pathway in order to contain global warming to an acceptable level. In order to achieve the 1.5 degree Celsius scenario pathway, governments, organizations and citizens have different ways, different climate measures that they can take. First of all, their policy instruments such as carbon taxes or ETS systems, the implementation thereof, demand-side solutions and supply-side measures, as well as investing into technology disruption and incentivizing the deployment of those new technologies. From an organizational perspective, organizations may first start by understanding implications of the 1.5 degrees Celsius pathway scenario for their own organizations and set clearly defined targets for negative emissions. Second, gather greenhouse gas emissions and growth data to be validated. Third, analyze absolute and intensity targets through use of online tools and/or external support. Fourthly, execute by determining and aligning internal systems, processes, incentive mechanism. And finally, disclose by communicating and reporting progress on science-based targets to stakeholders. When analyzing the greenhouse gas emissions of any organization, we can distinguish between Scope 1, 2, and 3. Now, Scope 1 refers mainly to the manufacturing of a good or the creation of a service. Scope 2 refers to the emission associated with heating, cooling, electricity, etc. Scope 3 refers to the value chain. Now, emissions along the value chain are a bit more complex and a bit more difficult to measure. What we are referring to here are the emissions from suppliers with regards to the creation of raw materials and their processes, the transportation of those goods to, let's say, a plant, the transportation from the plant to a customer, the use of the product itself, and the disposal of that product. As such, in most industries and with regards to most products, Scope 3 emissions are by far the highest amount of emissions. And as an example, in the retail industry, a highly emission-intensive industry, up to 80% of the emissions occur along the value chain. In order to offset carbon emissions along global supply chains, scientists have come up with various methods that would store carbon, CO2, in the oceans, in the soil, and also would allow us to technically remove CO2 from the atmosphere. They refer to this as carbon sink. Now, in order to implement those different methods and technologies, massive investments are needed. Goldman Sachs Research expects the cumulative 56 trillion of green infrastructure investments at present to meet net zero goals by 2050 if we want to achieve the 1.5 degree scenario, which in turn hopefully will drive technology and innovation around the world. When looking at the amount of carbon storage across the Earth ecosystems, one might be surprised to learn that it is the soils with a 2,500 gigatons that store most carbon across ecosystems around the world. The atmosphere stores about 800 gigatons and plants and animal life about 560. Now, another fact that is often overlooked is that it is the wetlands and not the tropical forest or the boreal forests which are most efficient in storing carbon. And also, as a general rule, the wetter and colder, the better. The world's forests absorb around 15.6 gigatons of CO2 each year. That's around 3 times the annual CO2 emissions of the United States. However, given fires, given deforestation, unfortunately, around 8.1 gigatons of CO2 are being leaked back into the atmosphere each year. First, what comes to mind is afforestation. So fighting deforestation around the world, in particular when looking at our large rainforest in the Amazon basin, the Congo, and also Indonesia. However, the reality today is that given the massive deforestation ongoing as we speak, the Amazon forest itself is not a carbon sink, but a source of carbon. Second, a popular concept is called BECCS, bioenergy with carbon capture and storage. BECCS refers to the process of extracting bioenergy from biomass and capturing and storing the carbon, thereby removing it from the atmosphere. So, in effect, we can not only restore the atmosphere, we can also produce energy simultaneously. Instead of relying on nature, many argue that eventually we will have to directly remove CO2 from the air, called direct air capture. Direct air capture technologies extract CO2 directly from the atmosphere and then aim to permanently store it in deep geological formations. One example is shown here. The scientists at Hellisheidi in Iceland set up a geothermal power plant, basically relying on the unlimited geothermal energy in Iceland, and argue that carbon capture in specific locations, such as this one, would be an excellent way to store CO2 safely in underground formation for thousands of years. Another big opportunity is to embody carbon in, for instance, building materials. This is an example from a company called CarbonCure that won the X Prize in 2018 by Elon Musk, which argues that recycled CO2 can be turned into fresh concrete, which will then reduce the carbon footprint of construction around the world. So imagine we would be building a highway or a high-riser, which by itself would allow us to remove massive amounts of CO2 from the air. Another way to look at this is direct injection of CO2 into, for instance, the soil or the seas. Now that would require a power plant or a chemical factory, such as the one shown before, that would then guarantee a direct stream into a basin, and that would allow the CO2 to be stored in an underground formation. A more futuristic way to look at CO2 removal is coastal carbon enhancement. The idea here is to accelerate weathering reactions of minerals that consume CO2 when they dissolve. That would allow pulverizing and distributing gigatons of these minerals onto land and enhance weathering, or C, which is called ocean alkalinity enhancement. That could eventually, as a process in itself, allow us to meet the 1.5 degree pathway scenario, given the size of our oceans and the length of our coastal. A similar idea refers to iron fertilization. similar in the sense that we could use the oceans and the process of iron fertilization as the intentional introduction of iron to iron poor areas of the ocean surface to stimulate phytoplankton production. This is intended to enhance biological productivity and/or accelerate CO2 sequestration from the atmosphere. Another way to use our oceans for CO2 removal at large scale refers to artificial upwelling. The idea here is the artificial upwelling would allow for using pipes or other methods that could be used to boost such primary production and increase CO2 removal from surface waters. Now, after having introduced a number of disruptive technologies which are currently being proposed, researched, invested in order to scale our CO2 removal from the atmosphere that would allow us eventually to reach the 1.5 degree Celsius commitment by 2025 as agreed upon in the Paris Agreements, I would like to now come to another policy tool which has proven to be quite successful and popular in 2021. That is to speak, the global carbon markets or emission trading systems, both in the compliance markets and the voluntary carbon credit markets. Now, emission trading shows enormous growth potential with voluntary carbon credits expected to grow exponentially across sectors, geographies. However, the supply of high-quality carbon credits remains a major challenge. The value of global carbon markets in 2021 totaled $851 billion and is predicted to increase continuously until 2030. In 2021, the EU was way ahead of other markets like the US or China, accounting for about 90% of the global value. Famously, Tesla's carbon credit revenues totaled $350 million in Q1 of 2021 alone. China, on the other hand, launched its own ETS system, emission trading system, in June 2021 for more than 2,200 power companies, emitting more than 26,000 trillion tons of CO2 per year. Carbon allowance prices have to reach a minimum of $200 per ton if we were to match the Paris Agreements, the reduction goals determined in the Paris Agreements by 2030. That is, of course, a very highly attractive target for many companies and for many traders that are interested in investing into that market. At the same time, the Chinese ETS system is supposed to extend to another 6 industries and is probably becoming the biggest in the world sometime soon, given the size of the industry of China and the emissions that are larger than the US and the European emissions together. As such, both compliance credits and voluntary carbon credits are supposed to increase 15-fold by 2030 versus the baseline of 2019 and by a factor of 100 by 2050. So how is this related to the topic of science-based targets? It is a highly interesting financial incentive to invest in technologies that would allow us to create scalable carbon credits, generate carbon credits that can then be traded either in a local or regional market or globally in order to offset global supply chains. So why has carbon trading become such an attractive sector? The European Parliament on March 10th in 2021, last year, backed a carbon border adjustment mechanism which would place a charge on the carbon content of emission-intensive goods imported into the EU from 2023 on, causing the EU ETS carbon prices to skyrocket. So what does that mean? Anyone producing a good in a place like China, say a manufactured good, now when importing into the EU has to pay for the offset of those emissions. The same is true for gas from Russia or iron ore from a place like South Africa or from Brazil. As such, companies around the world are now looking all over the place to find ways to source high quality carbon credits that will allow them to continue importing into the EU. The same is true for companies that have the headquarters inside of the European Union, as well as companies that are in a place like China, for instance, manufacture goods and are going to export them to the EU. Similarly, the brand new Chinese emission trading system has started to operate since last year, whereas the prices though have been relatively low, with an average of $6 per ton at average over the last year. However, the potential is huge. For instance, if you take China's building and construction sector, it accounts for 36% of global final energy consumption and 37% of energy-related CO2 emissions, according to United Nations Environment Programme. China represents 50% of the global sector and 25% of China's final energy consumption. In summary, here are takeaways. First, prepare for the implementation of science-based climate targets across the organization along the supply chain, similar to what has now become global best practice among Fortune 500 companies. Second, invest into disruptive technologies for carbon removal to implement carbon neutral negative emission goals inside your organization, but also along the supply chain. Third, get involved, prepare for global carbon trading, both for domestic and cross-border offsetting. As such, we wish you all the best for today, and please help build a better future. Thank you very much. In case of further questions, don't hesitate to contact us. Visit our website and please give us a call. Thank you very much. Bye-bye.